phonons, electron-phonon coupling and transport in solids. And let's go a step back and think about what you've learned the last week or the last 2 weeks. And when we were talking about crystalline solids, we were always exploiting and thinking about it in an idealized way, thinking about a crystal structure with a unit cell and then perfect lattice vectors that connect to each other so that you generate a perfectly symmetric, infinite array of atoms. On the other hand, what you also learned is that at finite temperatures, but even at 0 K due to quantum nuclear effects, everything is always moving. And this obviously implies that also this idealized picture of a static crystal with a perfect symmetry is only realized on average, but not at a microscopic level. So on a microscopic instantaneous level, the symmetry is always broken like you see here. The perfect periodicity is disturbed. And this has some very important consequences for many features of materials. So let's just give you an idea. So even at the equilibrium properties at 0 K, talking about lattice constants, cohesive energy, elastic constants, and so on, the small quantum nuclear effects, even at 0 K, slightly alter these lattice constants and give you inaccuracies if you don't account for them. If you go to higher temperatures, then obviously these vibrations have to be accounted for. So you have a failure to describe thermodynamic equilibrium properties if you don't account for these vibrations. This includes specific heat, thermal lattice expansion, phase transformations that all depend on the vibrations you have in the solid. And then you have an additional problem. If you try to describe thermodynamic non-equilibrium properties, these are also not accounted for in a static model. This would include charge transport, that means electrical conductivity, that implies heat transport, so thermal conductivity, how is energy transported due to the solid, or the coupling of charge and heat transport, so the Seebeck and Peltier effect. We'll come to that back later. And even the interaction with radiation, so X-ray, infrared, neutron diffraction is often dominated or has important features that depend on the vibrations in the solid. A side note to connect to the talk beforehand, you'll see here I'm always talking about conductivity and not conductance. This is a different physical effect. Conductance happens at a microscopic level. Professor Evers was talking about single molecules that get longer and longer. Here when I'm talking about conductivity, I'm really talking about bulk materials with length scales of the orders of centimeters or even meters. So and there are very different mechanisms that drive the conductivity with respect to the conductance. And we will come back to that later in the talk. Now, to highlight how we can calculate these different properties and what we need to account for it, I will actually use 2 examples. One example, everybody should know, this is semiconductor technology, this is silicon. And if you think about the giant steps that have been made in semiconductor technology over the last years, you see this has led to a miniaturization. From microscopic transistors in the 90s and 80s, we're now going to nanotransistors in 2015, where you have something like 10 to the power 9 transistors per centimeter square. And this miniaturization has led to very big problems, both in the design and in the manufacturing and the lithography of that. But in the designs of CPUs, one of the biggest problems nowadays is that you generate local hotspots at the nanoscale. So within your CPU, some parts get exceptionally hot, and this obviously degrades the lifetime of such a device. And in the design of the CPU, that has to be accounted for. So understanding how these materials behave in thermodynamic equilibrium under stress and how heat is transported that way at the nanoscale is a big problem there. On the other hand, I'll bring you the example of another material where the problem is just the other way around. These are so-called thermal barrier coatings, typically based on zirconia polymorphs doped with something, mostly yttrium. And this is a material that has a very, very low thermal conductivity. We'll see it's a very anharmonic material. And for that, it's used as a small coating, something like 500 micrometers, on top of the superalloys used in gas and combustion turbines like that. And due to the low thermal conductivity, this material insulates the underlying superalloys from the extreme temperatures that are generated during combustion in the gas phase. So 0.5 millimeter almost drops 500 K in temperature. On the one hand, again, this is a lifetime engineering process, so the superalloys are exposed to less temperature, so they have a longer lifetime. On the other hand, what you can do is you can drive up this operational temperature. And as a matter of fact, this is a process that has been driving fuel efficiency increases over the last 30 years in any turbines. So what people have done is, due to this insulating layer, they have been able to increase the operational temperature. Just for a Carnot argument, each 100 K you gain in combustion temperature gives you roughly 1% in fuel saving. So nowadays, whatever airplane you're riding, the combustion actually takes place at a temperature that is roughly 300 K above the melting temperature of the superalloy here. And the only thing that prevents a melting of the turbine is this 0.5 millimeter of ceramics. So obviously understanding, optimizing, and improving these materials here and lowering the thermal conductivity even further is an important job in the next couple of decades if you want to make air travel even more fuel efficient. So from that point of view, these are two edge cases that behave quite differently. Just discussing from a thermal conductivity point of view, this is a minute thermal conductivity, this is a huge one, and from that same kind of argument, you would argue that this is a very harmonic material and this is an anharmonic material. So they're driven by different interactions. And what I want to show you is how we can use first principles theories to really bridge the gap between these materials, describe both of them, what is important for what, and then get a qualitative understanding what has to be changed or what has to be done to improve these materials. So what will be the first step? Now, we will discuss the harmonic crystal. So I think you have seen that there are ways to discuss the dynamics of atoms on a DFT base, for instance, using molecular dynamics. Now, in a solid, we have many atoms. So molecular dynamics methods are desirable, but are typically very expensive. So first, you want to try to get an approximative description that gives you qualitative insight, even if it has some limits. And this is essentially the harmonic theory. And for that, you start with the potential energy surface. Obviously, in a real crystal, this is a 3n dimensional potential energy surface. Just here, you have this one dimension. And then you approximate this potential energy surface by a Taylor expansion. And the first term is obviously the static energy here in equilibrium. Then you get the linear term, and this one, does it appear? Yes. This is the derivative in equilibrium, so it corresponds to the forces that vanish. And then the next first non-vanishing term is the Hessian here in equilibrium, so the second derivative. And this would be the first non-trivial term that needs to be accounted for. So you already see what the main idea of this approximation is. You approximate the potential energy surface close to equilibrium, and this is also its limit as soon as you start leaving this equilibrium position. So you heat your system up and you're far away from here. You see that obviously such a parabola can no longer describe the potential energy surface. So essentially the harmonic approximation is only valid for small displacements at low temperatures. Now, you think calculating this should be trivial. These are just second order derivatives. Forces we have done all the time. What can we do to get the second order derivative? And this is actually not a trivial problem. That is not as straightforward as just going from the energy to the forces. There's an additional conceptual step that you have to make. If you just think about lecture 1 on the basics of electronic structure theory, we had discussed that the potential energy surface that the nuclei experience corresponds to the expectation value of the Hamiltonian. This is nothing else than the Born-Oppenheimer approximation. If you try to do the derivative to get the forces first, this is easy. You do the derivative, then you get the expectation value of the Hamiltonian, and then you get an additional term where you have a bra Hamiltonian, and then the cat of the derivative of the wave function. Now it's a trivial exercise to show that this second term vanishes in a Born-Oppenheimer approximation because we have a ground state electron density. So for calculating the forces, the only thing that we need is the ground state wave function or ground state density, but not its change under a nuclear displacement. So this is what you get already from a ground state calculation. If you go to a Hessian, however, what happens is that you get two terms. One times you get the second order derivative of the Hamiltonian and the expectation value of it, and that is easy to just compute from your ground state wave functional density, but then you get an additional term which involves the response or the derivative of the wave function. So this is a quantity that needs additional treatments that is not just trivially extracted from a simple ground state calculation. And as a matter of fact, this kind of argument can be generalized in the 2n+1 theorem. So if you require the 2n+1 derivative of the energy, then you need to have the end derivative of the wave function or electron density or the end response. So the first derivative of the density will give you the Hessian and even the third order force constants. If you want to go beyond that, you need higher derivatives of your electron density. Good. So you can calculate this Hessian thus in two different ways. In one way is to use density functional perturbation theory. So you really look at the perturbation of your wave function, you calculate that, or you use finite difference. Just let me give a short overview what the different methods do and what the difference is. If you do density functional perturbation theory, you really start from your usual density functional calculation. This gives you the density, and then you start to introduce a perturbation. Roughly speaking, you just move an atom and look what happens with the density. This will require an additional self-consistency cycle, one consistency cycle for each perturbation, and this will then tell you how the electronic structure will change if you slightly displace one atom. And you see this would be such a calculation, and you see that the density response, so this derivative, is localized around the perturbation. And then from all the sum over this all couplings, you can calculate your phonons, as we will see later. The interesting thing is that this response is localized in real space. So it is not too efficient to use techniques that are designed to treat non-local periodic stuff to calculate something that is localized. So it's typically you have to switch from a periodic representation to a localized representation to get these things accurate. One example, what is typically done, is that you compute your response in reciprocal space first on a rough grid in the Brillouin zone. Then you transform it to real space. You localize it there and make a real space interpolation there, for instance, using Wannier functions. And then you go back with a Fourier transform to the reciprocal space so that you get a fine spacing on the Brillouin zone of this kind of properties. But you can also use a more straightforward approach. You can also treat everything in real space. So this is an example. So just giving you an idea how this is done in FHI Ames, where real space is used by default for all computations. I don't want to go too much over the details, but just showing you a little bit the idea how periodic structures are dealt at all within the internals of FHI Ames gives you an idea what are the bottlenecks and what is done at which point. So the first thing that you need to do is, obviously, if you are working in real space, to apply the Bloch theorem. So each orbital gets a phase that is related to its distance from the original unit cell. And then, you obviously, if you want to calculate something like a Hamiltonian matrix, you have to calculate all these kind of integrals of all periodic replicas that interact with the one in the unit cell. Now you see immediately that this is an unbound integral, and that you have a lot of different atoms that you have to account for, even if you just want to integrate this one thing. So just give you an idea for 1D, 2D, or 3D, even if in the unit cell only 6 2 and 2 atoms are included, if you actually want to perform these integrations, you would need to account for 66 to 100 or even almost 400 atoms that in some way interact with the unit cell. So this is in part circumvented in the internals of the code by rewriting this unbound integral that is numerically not desirable into an integral just over the unit cell, and this changes then the sum to a double sum over a reduced set of periodic images. And what does this mean? If you just look at something like an overlap or a Hamiltonian, what you would like to do is to integrate over these two functions, but you want to integrate just over this unit cell here. So to get such an integral, you just sum up over different copies of these pairs that you shift and shift and shift, and always just sum up over the unit cell. And this gives you the complete integral in the end. So this is done already at a normal DFT level, and this is also why you might have noticed that doing a periodic calculation is typically more expensive than doing a simple molecule calculation with the same number of atoms. But you see, this is then the supercluster that is accounted for, but you have all properties now in real space. You can even increase it to make really a supercell that has Born-von boundary conditions. And if you compute everything there at once, you get all couplings of all electrons and all nuclei with each other in this extended kit. And if you do that, then you get all non-vacuuming Hessian elements in real space, and then you get all properties in reciprocal space just by Fourier transform, without interpolation, without truncating Fourier transformations, without any approximation. So here this gives you really all the couplings of each electronic state with each nuclei at once. So this gives you just an idea where you can apply that. You can do simple molecules, 2D and 3D, and this is just a validation that this kind of approaches work. Give you a little outlook, and this will come at the end of the talk. This is not just phonons that you get here. Due to treating really the complete electronic structure, you can get insights on really all electron-phonon couplings at once, and we will see the usefulness of that at the end of this talk. Let's come back to the phonons themselves. Another much more simpler way and conceptually more intuitive way to calculate this Hessian are finite differences. What does this mean? Essentially, you approximate your Hessian by saying this is the derivative of your forces, and you then just calculate the force for a displaced atom and use this differential quotient to determine that. So trivially, this would give you a lot of different calculations because you have to displace each atom at least once. But if you, in this example, for instance, you use symmetry to not calculate everything, but you look at which elements should be equal due to symmetric reason, this reduces the problem from 36 different constants that have to be computed to only 5, and for that it is sufficient to just displace one atom. As a matter of fact, you will learn to do that in this afternoon during the exercise and during the tutorial. This will be exactly the system you will be studying to learn how to do that with finite differences. Once you have that, you can just compute the vibrations, and this is conceptually very similar to what you have done in the practical session 1 for molecules. You have n atoms, you have 3 n degrees of freedom, and a Hessian that would scale with 9 to the n to the power 2. Now, obviously, if you go to periodic solid, n goes to infinity. So what do we have to do here? So, and here, again, we use the reciprocal space representation to circumvent this problem. Just think about such a linear line or linear chains of atoms where you have one unit cell that is connected by lattice vectors, and the real space Hessian with I and j going to infinity can be Fourier transformed back to the unit cell, and then you get a dynamical matrix where the I and j just scale with the number of atoms in the unit cell, and you get a continuous variable q that describes how these properties change in your Brillouin zone. Now, if you look at it, this is the exact same problem that you've treated in electronic structure theory. So instead of looking at a Hamiltonian that is of infinite size, this Fourier transform maps this to a finite Hamiltonian or finite matrix that you then have to solve for an infinite amount of Q points. The nice thing is that it's often sufficient to just use a finite amount of Q points, and the rest you can interpolate. And that is why this is a strategy that is numerically successful. Good. Once you have this dynamical matrix, this converges quite nicely typically, because the interactions obviously fall to zero if you have atoms that are very far away from each other. So at some point this Hessian has to become zero, because if you move one atom here and the other 2 meters away, there is no more interaction. So you can really get an accurate representation, and then you get this whole dynamical matrix in a reciprocal space. From that, you can just use that, and you can see that in this potential, the equation of motions become an eigenvalue problem exactly of this dynamical matrix. You have to determine these eigenvectors and eigenfrequencies by just solving this problem, and the solution is nothing else than a sum over harmonic oscillations with this frequency. And to give you an idea on how this looks like, so this would be such a typical solution along a reciprocal space. What you see at gamma, obviously you have this phase factor vanishing, and what you get are 2 different type of modes. There is one where everything is in phase, and you see also the atoms in the unit cell are in phase. This is a so-called acoustic mode. So, and you see that this would correspond to just a translation of the crystal. And with that, this can give you no energy gain. The frequency has to vanish. It's zero. And then you have an additional mode, the so-called optical mode, in which, again, the individual cells are in phase to each other because we are at gamma, but the actual atoms in the unit cell with respect to each other, they are vibrating against each other, and this gives you a finite frequency here. If you go on the other extreme, on the boundary of your Brillouin zone, then the phase changes quite dramatically. You get a phase change over each second a unit cell, so you have a very rapidly oscillating phase change, and this gives you quite different modes. So in the acoustic case, the atoms in the same unit cell are still in phase, but the neighboring unit cells are out of phase. So this gives you a compression and expansion of the neighboring unit cells, and with that also the acoustic mode gets a finite frequency. And the same applies for the optical mode. Also there you have a switch in phase, but now you see these are still very much similar motions, so the actual dispersion, so the actual change in frequency when going to the Brillouin zone is not that dramatic. So if you go to a real crystal that is not as simple as the sketch here, you will always get 3 acoustic modes that correspond to the 3 different translations that you can have in different Cartesian directions, and then 3n-3 optical modes for your system. Just to give you an example, this is the vibrational band structure of silicon. You will calculate this this afternoon. From such a band structure, you can calculate also density of states, exactly like you've done in the electronic case, but this time integrating over these vibrational frequencies. And then you get the exact same kind of properties like that will be discussed more in the afternoon. One interesting thing, if you have the density of state, you can evaluate the free energy. So how does the motion of your nuclei change the free energy as a function of temperature? And for that, you have one term that essentially corresponds to the 0-point vibration, plus one additional term that scales with temperature, and these are the thermally induced vibrations. And from that, you get such properties as the free energy, or for instance, its second derivative, the specific heat, which gives you this nice behavior that you know from textbook, the T/3 dependence here at low temperatures, where only acoustic modes play a role, and then where this classical limit at very high temperatures, we start to approach the Dulong per T limit, and the contribution to the specific heat is constant with respect, or scales with the number of degrees of freedom in your system. Good. So far for the basic theory. What can we really do with that, and what can we learn about that? Let's go back to the zirconia I've told you before. So this system has three different phases. You have a monoclinic structure at very low temperatures, a tetragonal structure at medium temperatures, and if you want to know when and how this phase transition is happening, you need to account of the free energy. So what you need to calculate is not only the energy of these individual structures at a ground state level, but also how the nuclear vibration changed it. And if you look at the difference of that as a function of temperature, you see that this is a falling function. So you see that the tetragonal structure becomes more and more stable with temperature. And you have this change of sign at roughly 1500 K. And this roughly corresponds also to what you observe experimentally. So you have this phase transition due to the nuclear motion at 1600 K. Still, be careful. I've told you before, the harmonic approximation is only valid at low temperature, and it can become inaccurate and terribly misleading if you go at higher temperatures. If you would like to do the same kind of approach for the tetragonal and cubic transition, for instance, where we're already at temperatures above 2400 degrees Celsius, then you end up in very big problems. You see that the frequencies become negative. This indicates that you are actually not in a stable geometry anymore. What is happening here is that you actually have this cubic structure that is a saddle point of your potential energy surface and not longer a minimum. So what you can imagine is that actually you're sitting in this tetragonal structure, and you can obviously go from one tetragonal structure to the other, and in the middle you have this cubic structure. Going to a 3D representation, this gives you something like this different displacements, how this tetragonal structure can be arranged, and the potential energy surface then also gets two-dimensional. You have different minimas, and you have in the middle the saddle point belonging to the cubic structure. And what you actually observe if you run molecular dynamics on the system is that your atoms really are jumping from one minima to the other. You can observe that here, that this blue line changes sign, so you're jumping from one way to the other here. You're running around in circles, and if the actual experimentalist is going to measure this material, even if you're running around in circles here, for him on thermodynamic average it will look like as if the atoms are positioned here in the middle, even if this structure is never realized at a microscopic level. So here you already also see this is something that you cannot treat with a harmonic approximation. Just doing a simple Taylor expansion around one of these minima will not really help getting any insight on the thermodynamics that happens at these high temperatures. So just to give you an idea or to summarize this part, we see that when you go to high temperatures, you have to be careful, and then there's no way around of using molecular dynamics. All these approximate treatments will fail. Before going further in that case, let me just also give you a little bit of outlook of what you will do in the afternoon. One can improve on the harmonic approximation by doing that in a quasi-harmonic way. One failure of the harmonic approximation is, for instance, that you cannot account for lattice expansion. And this is very simple to understand. Your Hamiltonian just depends on the force constants. This does not depend on the volume, so the derivative is 0. So there is no lattice expansion at all. You can somehow, on hindsight, introduce this volume expansion by looking how the force constants change with volume in this so-called quasi-harmonic approximation. In principle, this approach is very simple, and it's very it's related to what you've already done in the practical session 2 when you have done Birch-Moynihan fits to calculate the lattice constant at 0K. In this case, you do the exactly same, but you don't only calculate the total energy, you also calculate how the force constant change as a function of your lattice constant, and then you can add the free energies, for instance at 0K, to see how much the lattice constant changes due to zero-point motion or at different temperatures, and you can again fit with the Birch-Moynihan equation to get the temperature dependence of the lattice constant. And if you then calculate its derivative, so the lattice expansion for silicon, you get this very nice curve, and you see silicon has a negative lattice expansion at low temperatures, and this is exactly what you're gonna discuss this afternoon, and hopefully at the end at dinner tonight you will know why this material has this very interesting and peculiar behavior at low temperatures. Good. This essentially summarizes already what I wanted to tell you about thermodynamic equilibrium. So harmonic approximation is a very efficient approximation. It works well, and it can be very useful to get qualitative insights at low temperatures. It's also computationally very rapid, but it fails and it becomes increasingly inaccurate at elevated temperatures. And this brings me to the transport processes and transport coefficients. Here we will see this is an area where the harmonic approximation fails from the start. And when we talk about heat transport, let me stress that again. We're talking in this talk about a macroscopic effect. The usual thing you observe in daily life, you have a macroscopic bulk, there is a temperature difference or temperature gradient, and then a heat flux naturally develops and tries to reestablish thermodynamic equilibrium. And the way this is measured is through Fourier's law. You have a heat flux that is related to the temperature gradient, and the proportionality constant is the thermal conductivity, and this obviously is a constant that depends on temperature, on pressure, and on the material that you're looking at. There are actually 3 contributions to this thermal conductivity. You have photons. If you're at very, very high temperatures and your material is transparent and you're essentially incandescent, then photon can start transporting light through your material. The materials we are looking at, that is not particularly interesting. Similarly, you can have electrons. We'll go back to that at the end of the talk. Now we will look at insulators, where electrons are essentially not contributing to the thermal conductivity. And then the only thing that you have are the nuclei, and we are back to describing the nuclear dynamics. Now, the harmonic approximation fails in describing heat transport. Why? We had seen this is second order Taylor expansion gives you this very nice description in terms of phonons. But the one thing that makes this harmonic approximation so efficient is that in this harmonic approximation you get decoupled normal modes. So it transforms the problem of having 3n coupled degrees of freedom in solving 3n independent equations. And with that, the phonons don't see each other. And this leads to an infinite lifetime. In a harmonic approximation, if you set up one mode to transport a certain amount of energy, it would travel for an infinite amount of time. And this leads to an infinite thermal conductivity. Only if you account for anharmonic effects, then you start getting phonon scattering and anharmonicity. So then, at some point, the lifetime of your phonon gets limited. And again, to account for that, you need electron-phonon coupling that describes how this potential energy surface change as a function of your displacement, and that introduces phonon scattering. And the formal tools to do that are again using molecular dynamics and perturbation theory, and I will show you how we will connect the two. Before getting there, however, let's first get an overview what the kind of length and time scales are that we need to discuss. If you think about typical vibrations in a solid, the period is in the order of picoseconds. That means if you want to measure something like anharmonicity or like scattering, that happens maybe all 100 periods or even all 1,000 periods. If your system is particularly harmonic, you have to average up to nanoseconds. And if you translate that in a length scale, how far your phonons will have traveled, and then this translates in something like microns. And this is obviously the domain where typically semi-empirical or classical potentials shine. Going to this kind of area with first principle methods is challenging. There, we're typically limited to just much smaller time and length scales. And this is one of the effects that is typically challenging when treating this kind of transport problem, because you have to find ways to extrapolate to the limit where you really reach this long time and length scales. And one way to do that is to work directly in reciprocal space and using a Boltzmann transport type approach. I'm not going over the derivation itself, but the equation essentially describes how a phonon population evolves over time and how this changes due to scattering events. And the actual result for the thermal conductivity that is quite involved to get, but it's very intuitive. The thermal conductivity is nothing else than the velocity each mode moves times the energy it's transporting, and then times the lifetime. For how long can this mode survive until this mode breaks down? And these group velocities, these frequencies, and these equilibrium populations, this is something that you get immediately out of harmonic theory. And as I've told you before, the phonon lifetime is the challenging thing. This you can get, again, out of density functional perturbation theory by going one step further and doing additional perturbations. You can try to fit forces from ab initio MD. You can fit phonon line weights from ab initio MD. These are strategies to incorporate more anharmonicity into these approaches beyond the one of just doing simple perturbation theory. All of these approaches give very good thermal conductivities at low temperatures for good thermal conductors, where essentially the harmonic approximation holds and anharmonicities were really just a perturbation of this thing. But if you go to high temperatures, this kind of approaches become questionable. So just to summarize that, if you use a Boltzmann transport equation, you're typically limited in the accuracy of your interactions because you're treating everything perturbationally. You cannot go to high order perturbations. So this is applicable at low temperatures. But the finite size effects are minute. You're working in reciprocal space. Everything works fine. And even disorder or defects can be treated in additional parametric models. If you want to go to high temperatures, you typically would like to use molecular dynamics so that really all interactions are accounted for. The most simple way to do it is to use non-equilibrium molecular dynamics. This is a very straightforward and intuitive idea. You take a long system, you apply one thermostat here and one thermostat here with different temperatures, and then you let your molecular dynamics run, and what you obviously will get in the steady state is a temperature gradient between these two thermostats. And if you look on how much energy then travels from one side to the other, and you plug that into Fourier's law, you can extract the thermal conductivity. This is easy to set up in an afternoon, but if you then start calculating, what you discover is that actually your thermal conductivity has a distinct dependence on your supercell size. So these are a calculation for a classical potential, silicon and diamond, and what is shown here is 1 over the thermal conductivity over 1 over the size of the supercell. So, and the bulk limit is down there. And what you see is that this resistance has actually two contributions. One that is intrinsic to the bulk material, and the other one that comes from the scattering at the boundaries of your supercell where you have your thermostat. So what you need to do is running calculations for larger and larger and larger supercells, and then you could, in principle, extrapolate down to the bulk limit. Now, I've shown you these are for classical potentials. if I try to plot that on the typical length scale here in green that I would use in first principle calculations, you see we are on a completely different order of magnitude. So you would need to extrapolate from something that is in the order of 1 down by 2 orders of magnitude. Now, this is first numerically inaccurate and really, really tricky to get it accurately. The second thing that happens here is that here you have extremely large temperature gradients. Just think about it. If you do a supercell of something like 10, 20 angstrom and just apply a temperature gradient of 10 K, this will translate into a temperature gradient of the order of 10 to the power 8 or 9 Kelvin per meter. And these are temperature gradients that happen on the surface of the sun, but not in your materials as you have them in your laboratory or in your applications. So this kind of approach works nicely because you can really account for the full order of interaction. You can go up to all temperatures, but the finite size effects are so huge that reaching the bulk limit is really, really challenging. You can use it if you're looking at nanostructure, if you really just study something that is in the order of magnitude of nanometers, then you can start using that, but otherwise reaching the bulk limit is challenging. Exactly because you use thermostats to apply this non-equilibrium situation. And this brings me to the last method that is based on equilibrium molecular dynamics. And it's based on the fluctuation dissipation theorem. And that is one theorem that has been discovered quite a couple of times, 2 or twice in the last century. And the first mention of it is in Einstein's seminal paper of Brownian motion, where he discusses the random motion of particles in a fluid. And in a footnote, he mentions that in future work, someone should look at on how the friction in such a liquid is related to the diffusion constant, because he is convinced that the friction will be proportional to the actual diffusion coefficients, or to the force that this particle experiences when being dragged through to such a fluid. Formally, it took a couple of decades longer to bring that down on something like a 20-page thermodynamic formalism that is mathematically correct. But essentially, this is exactly the intuitive idea of Einstein. If you're interested in transport processes that happen in non-equilibrium, it's sufficient to look at the fluctuations in equilibrium, because the actual magnitude of these fluctuations and the lifetime of this fluctuation will be related to these transport coefficients. Now, this implies that you can do simulations for thermodynamic equilibrium, which will give you some information about non-equilibrium processes. And this is not obviously helpful. So in the case of the thermal conductivity, you need to monitor the heat flux in thermodynamic equilibrium, and then the integral over the autocorrelation function will give you the actual thermal conductivity. Putting that on a more hand-waving side to see what is actually happening, just think of a macroscopic model. So we start with something that is completely cold beside this delta function with a defined temperature here in the middle, and then we look what would this evolve. And what you would see is obviously this is described, such a temperature distribution is described by Gaussian, that it gets broader and broader and flatter and flatter. And if you look at the flux, the average flux in the volume, you see that this would decay down. And in the exact same way, the autocorrelation of the flux also gives you such a decaying function. And if you would just solve that for this kind of expression, you would see that this is exactly proportional to the thermal conductivity. And in this macroscopic case, this is very simple. The interesting thing is that the exact same happens if you look at disorder system like in our molecular dynamics case. In that case, you don't have such a nice temperature profile. Actually, you have huge fluctuations that go over each other. And also, if you look at the heat flux itself, this is something that is oscillating. You have heat going from one place to the other in your supercell. But if you calculate the autocorrelation function, you get again something that is smooth that you can integrate over to get your thermal conductivity. Now, how can we do that in a real ab initio approach? So what you need to do first is to define a heat flux. This is technically quite involved. We would start from a continuity equation that relates the local energy to the local heat flux. And then if you integrate over it, you get your heat flux in your unit cell. So typically what you would do is to decompose your energy, saying each energy is somewhere at some atom. And then if you integrate over it, you get a heat flux that corresponds essentially to the time derivative of something like an energy barycenter. The problem is that such a definition requires a decomposition of the energy, and that is not unique. Even if you think in a classical potential you have two atoms interacting, does half to it belong to one and one to the other? Seems intuitive, but it could even be 1/3 or 2/3. It can go whatever thing you like. You can try to generalize that in a first principle fashion, then you get a very similar expression for an energy density that is just an integral expression, but for the exact same, and you get a heat flux that looks like that, but for the exact same region you get energy densities that are not Gaussian independent. You can always add a rotational field to your energy density and you will get the exact same result. And so this brings you into problems to treat that. One way around to do that is to go from this simple definition of the heat flux to looking a little bit more at the details and looking at what is really happening at a microscopic level. If you take this time derivative into the sum, you get two contributions. One is velocity times energy. This is called convection. This is happening in an ideal gas or liquid. You have one particle that is hot and is traveling from one part of the room to the other, and then it heats up the other room. And this is actually what is driving thermal conductivity in this room, in the gas, why it's hotter up there where Volker sits than down here where I am. But in a bulk, no atom travels on average. If you don't have diffusion, everything stays where it is on thermodynamic average. And then you can neglect this contribution. And what you're left with is essentially the derivative of the energy times its position. And the interesting thing, this derivative of the energy is unique. I'll spare you the actual derivation, but what you can actually show, this derivative over time translates in a derivative over position, and with that you get forces. And in contrast to the energy, a force is always well defined. You know how much force is acting on an atom. There is no Gauss dependence on the force inside. Also, this kind of heat flux describes phonon transport. If you think about the whole phonon formalism, this also does not account for mass transport. And so this is also well defined for classical potentials and in first principle frameworks. So for the sake of time, let me skip the actual derivation of that. What we actually will jump is just to the final result. What you get is that you can go over all the Hellman-Feynman theorem, do your derivatives, and then you get an expression for the heat flux also in this first principle approach. As you see again, this is just from if you remember how Hellman-Feynman forces look like, this is essentially force times distance again. And this is nothing else than the internal stress of the system. So how much work does your atom do against the field of all others? This is something that you can implement, that is already implemented in FHI Ames. We have the analytical stress has been used, for instance, in tutorial 2. And you can use that. I'm not going over the individual formula, but you see if you look at them, they have the exact same kind of structure of derivative times distance. And if you do that, then you can apply that, and you can really look at thermal conductivities, and you can calculate this. And this is, for instance, one result for zirconia. You can compare that to a semi-empirical classical calculation. This immediately shows you that you're doing better than them. That is not too surprising. We're using a much better description of the interactions. But what it also shows you here, this classical potential was not able to go anywhere beyond 1500 K. The simulation would just explode. While when using a first principle methods, you can really go from room temperature up to the melting temperature of the material without any additional involvement. Now, to close the talk, essentially, let's think about, again, what this kind of effect is. We'd seen in the very beginning that silicon had such a huge thermal conductivity, and zirconia has such a low one. So it's obviously nice that we can reproduce this low thermal conductivity, but you're not doing theory to reproduce the experimentalist. You're doing theory because you want to know why this is happening. And this brings you again back to the plot that I've shown you before, where I've said at high temperatures you start to have these switches between different minimas, and this is again related to the fact that the harmonic approximation breaks down. And with that you get strong anharmonic effects whenever you switch from one minimum to the other in this material. And you can then, if you start understanding that, you can start tuning that and looking how much would, for instance, a defect change your thermal conductivity. So what you can, for instance, do, so these are the plots for pristine zirconia. You can add vacancies which show you that you can reduce the barrier, and with that you would increase anharmonicity because these jumps or switches would become more frequent. You can add yttria and the vacancy, which would slightly distort the topology and also give you slightly different barriers. And you can even add additional dopants that allow you to increase the barriers if you want to increase the thermal conductivity. And just as an example how this correlates to real measurements, if you look at your thermal conductivity as a function of the doping, what you see that it goes down quite significantly. And this you can correlate again with the barriers that are present as a function of the doping. If you introduce yttria in your system, what will happen is the barriers go down, so the probability of such a switch becomes larger, so the system becomes more anharmonic, you get a lower thermal conductivity until at some point. At some point, your doping has become so strong that this situation with different minimas is annihilated. You get really a true new minima at the cubic state. This is roughly at 17%. There you have a fully stabilized cubic system. And then at that point where one real minima starts to exist again, you also see the thermal conductivity starts going up again, a harmonic approximation goes better and better, and also the thermal conductivity becomes larger. So in a nutshell, this I should have shown you that you can also tailor anharmonicity by doping. And with that, let me go to my summary, which is essentially, if you look at different kind of approaches, they have different pros and cons. Something like a Boltzmann transporter course is very accurate for and rapid for almost harmonic materials. If you're treating nanoscale issues, then you can go with a full MD approach to get stuff at all kind of temperatures. But if you need bulk materials and high anharmonicity, there's no way around of using equilibrium molecular dynamics. And with that, I hope I gave you a little bit of an overview what is important, what is interesting in this field, and I'm looking forward to your questions.
Thank you very much.